All right, welcome to this is the velocity modeling overview for Decision Space 10ep.3. My name is Larry Fink. I'm the velocity modeling product manager, and I'm excited to talk to you guys today about all the new functionality and features in velocity modeling for 10ep.3. Okay, before we get started, I just want to stress how critical the velocity model is, how critical it is to have an accurate velocity model in the exploration and development workflow. Essentially, velocity, it is the bridge between time and depth, and we want to get to depth, and we need an accurate velocity model to properly get to depth. If we don't have the accurate velocity model, our structures can move up and down. The oil-water contacts could change in between the wells. The structures move laterally. We'll have to change well plans. The structures and layers get stretched and compressed improperly without the accurate velocity model. So needless to say, it's a very important part of the exploration and development workflow. So what did we do for EP3 that's new and exciting? We did four major things, the first of which is usability updates. And essentially, a lot of these are basically common sense velocity modeling utilities that we can use in most velocity modeling scenarios. And I'll go over the specifics in just a minute with a live demo. Okay, and let me get that out of the way. The next big feature, we added and enhanced the depth stretching workflow. And this is really good for deep water subsalt exploration workflow. Okay, and salt just super affects the domain conversion and the stretching, and we've added some great features there to increase the workflow's time, disk space, and money for when you're deep water drilling. And I'll go over the details of that in the demo as well. Probably the biggest thing we did is this regional geostatistical velocity modeling. And in this case, this is where we don't have a ton of velocity data, but we want to get the best possible velocity model in a basin-wide or petroleum systems size model. And we've done a lot of great features there, and I'll go over a lot of those details with the demo as well. And then the final big feature that we have is what we're calling velocity zone analysis. And this, again, we want to provide the best velocity model possible in the case where we do have a lot of data. This is sort of our overdetermined case where we have tons of data, but we want to make sure we get the velocities correct inside the layers. We just don't want to use constant velocities inside the layer. We want to figure out how the velocities are changing vertically and laterally within the layers. Okay, so without too much hesitation, let's go into the details of the usability updates. And the first big thing we added was, the functionality to make true layer cake models. And essentially, this is actually replacing some of the old Depth Team Express functionality that we've had for a while. But here, we'll just give it a time surface and a velocity surface, and that gives us a velocity model. And of course, you stack a whole bunch of them on, you get a multi-layered layer cake velocity model. Very useful in lots and lots of workflows. We added back the dynamic time to depth dashboard. This is actually replacing some old SizeWorks functionality that was used in a lot of the real-time drilling type of workflows, and I'll show this in the demo as well. And another piece of Depth Team Express functionality that we replaced with this release is just the usability of displaying the velocity overlays onto any surfaces. And I can show that and tell you why that's important in sort of a live demo here. Okay, so essentially, if we have a surface, any kind of time or depth surface, and we're curious about what the velocity is along that surface, we just added it now as an attribute that we can overlay. You just select the velocity model you want to overlay, and you toggle on the overlay button, and boom. Now, instead of looking at the structure, you're looking at how the velocity relates to the structure. And what we want to do here is when we look at this, we're looking for, okay, are the velocities conformal to the structure? Is there perhaps a down dip strat trap that's shown by maybe a low velocity zone that doesn't conform to the structure? Are there any types of anomalies that might be showing up here? So it's a nice way to see, okay, do I have a decent velocity model, overlaying it, very usable, very easy to view in QC. Now, with the dynamic dashboard, we can jump through a whole bunch of different wells and look at the time-depth relationships. But if I'm talking to my drilling friend and I say, oh, you know what, you need to be looking at 2 seconds, well, he doesn't know what 2 seconds means. So all I have to do in my dynamic dashboard is type in 2 seconds, and that will immediately tell me, oh, that's 9,081 feet, okay? And then he says, well, you know what, Mr. Geophysicist, I'm actually at 10,000 feet, and so I type in that number, and it's going to tell me, oh, on my view as a geophysicist, that's at 2 seconds, 153 or 2153 milliseconds there. So it allows us to interact. So also in the dynamic dashboard, we added additional well information, so we can check out the datum information, Kelly bushing, and other features. So again, just helping out some basic velocity workflows there for the usability. All right, now if we move into the sub-salt drilling workflow, where the scenario here is I've drilled a couple deep water sub-salt wells, but the problem is my wells do not tie my seismic. There's lots of reasons why the wells don't tie the seismic, and I won't go into all those reasons, but the big deal is we want to be able to correct the seismic to tie the wells fast and efficiently, okay? And so we've added this depth workflow that we can just input a set of surface picks and depth horizons, and that will give us a nice relationship where we can tie the seismic depth to the well depth. And I want to stress very clearly that, say, like my green line here is the seismic depth. Now, just because a volume of seismic data is labeled as depth, that doesn't mean those depths are correct, okay? What's correct, we believe, are the well depths. So in the depth stretching workflow, all we want to do is we want to stretch these green seismic depths to the proper well depths, okay? And then once we do that stretching, we can get a more accurate interpretation and prediction of my tops, either pressure tops or actually drilling target tops. Okay, so it's important for safety as well. So to run this, it's a simple mouse button 3 on a depth volume. You select depth stretch. You define your picks that you want to tie to, and it runs very similar to just time depth conversion, but instead of going from time to depth, we're going from bad depth to good depth, okay? And bad depth meaning untied seismic depth versus well-tied depth, okay? So it's a very simple workflow, and it allows us to not have to re-depth migrate the data, which could be $500,000 to do a re-depth migration. If all we're worried about is around this well, we can do this stretching and think we get a pretty accurate view of what the seismic should be looking like. And we can do this very quickly. We also have a QC view of what the depth stretches are that we can volumetrically see, okay, are those stretches reasonable, and is it showing a trend in any form? Okay, so very, very good for predicting pressure tops and regular tops and subsalt drilling. Okay, now moving on to the third of our fourth big feature is the geostatistical velocity modeling. And again, this is very good to build the best velocity model possible when you have a limited amount of data. Okay, we're building these giant models with only a little bit of data. Okay, a big thing that we've done here is we've now allowed the support of multiple 2D and 3D seismic survey inputs. Previously, we could only use one survey as input. Now we can have multiple survey inputs, however big or small they are. They're typically not that big with respect to the basin, but that's fine. But it's great new functionality. We've also added the functionality for kriging and co-kriging of the velocities with lots of user control that's new functionality that we didn't have in any of our systems before. And this makes the geostatistical velocity modelers very, very happy that we now have this functionality. And the other big piece of functionality in this workflow that we added was uncertainty modeling. So this makes our reservoir simulation guys very happy that we can give them a P10, P50, P90 velocity model where they can run their different volumetrics on these different scenarios of velocity models that actually all tie the wells, but in a little different way. And I'll go through a demo of that in just a minute. But first I want to show what is the actual geostatistical velocity modeling workflow. We've worked a lot on this with our clients, and we've mapped out all the steps, and it's really just 14 steps. So I think, oh, that's pretty easy, right? Well, it's actually, it can be a bit overwhelming if you're not sort of skilled in the art of velocity modeling or geostatistics, and it can be a little overwhelming, even though it's a very detailed workflow steps, because you need to do a lot of features in different disciplines. We need 2D geologic mapping. We need seismic analysis well ties from the geophysicists. We need geostatistical analysis. We need velocity modeling analysis, and we need to do a lot of looping. Okay, so I agree it can be a little bit overwhelming, this workflow. So let me simplify it for you to make it very clear as what we're trying to do with the geostatistical velocity modeling workflow. What we're trying to do is correct the times in orange, and then we try to correct the velocities in blue, and then we finally tie to the depths in red. So all we're doing is some iterations to, we have this triumvirate of time, velocity, and depth. And, how do we solve for three things at once? Well, we're going to first solve for the times, then we're going to solve for the velocities, and then we're going to solve for the depths. Okay? And then I think this makes it much clearer how the workflow is actually going to go. So let me demonstrate the first steps of the workflow of how do we solve for the times in velocity modeling. All right, so let's take a peek at that. And again, this is a big regional prospect, say, and all we have in this case is some 2D seismic data. I've got, 5 or 6 2D time seismic lines. What I can do is interpret my main velocity structures, and you can see, oh, that's a pretty good interpretation there, right? Okay, but that's all the data I have for my time is just that over, possibly a million square kilometers. All right, so how do we make this an accurate time interpretation? Well, luckily we have some of the best gridding and interpolation algorithms in the world, so we can launch our 2D mapping solution here, and I can very easily go through some analysis on my input time interpretation, define what algorithm I want to use, run it, and voila, I now have a really good time interpretation. Okay, I've got a time surface showing up here. Okay, the question is, how accurate is this? Is this, a good interpolation, right? So we can look at that, and the way we find out if we think it's good or not is, does it tie the wells? Now, typically, we would do a well tie workflow to tie the seismic time to the wells, but because our seismic doesn't exist where these exploration wells are, we have to do a different method, kind of a poor man's well tie workflow. And what this workflow is we're calling a delta time analysis, where we take only the wells that have VSP data or check shot data, so they have time depth relationships with these particular wells. We look at where the picks are and do these picks tie the time interpolation that we just did with 2D mapping? And looking at this, I can see no, they don't tie. Some are close, but they don't tie exactly. So we want to get them to tie as close as we can in time before we go forward to look at what we do to get the velocities to tie. So we go into our geostatistical velocity modeling workflow, and we associate the times and depths in what we're calling a delta T analysis. And what we do here is we compare the 2D mapping interpolated times with the check shot times, and we get what's called just a delta T here, and we can see I'm 46 milliseconds too shallow here, I'm 23 milliseconds too deep on this particular well. Okay? So when we know that information, what we can do is write that out to a point set, okay? And I can display that point set in my same view here. And now what I want to do is I want to snap my original time surface to these updates, okay? And so I just set my parameters. I can go through all the, data QC that's involved in geostatistical modeling. I can, provide a variogram if I would like to do that. But simply I just push run, and boom, at that instant, I now have my time surface actually tied to my check shot data. Again, I don't have seismic out here, but I'm able to guide my time interpretation to fit this exactly. So this makes us pretty happy that we think we've got at least as close and accurate of time interpretation as possible. Okay? So that was step one of the workflow. Now step two, we're going to take these new time surfaces and try to figure out what the velocities are in between the surfaces, so the layered velocities between each of the surfaces. Now the velocity information that we have that regionally is really just coming from the 2D seismic data, okay? And that's from like the stacking velocities from the 2D seismic. So I'm going to start at the second layer because it's more fun to look at the second layer than the first layer. We can look at the updated time interpolations for our main velocity surfaces. So these are the layers that we want to use for our velocity analysis. And then what we do is we go into velocity modeling into our geostatistical workflow, and what we're going to do is we're going to define the 2D seismic data, as many seismic lines and volumes that we have. We can add those in. We could even add in extra 3D. Oh, sorry, I hit the wrong button here, and I will have to speed back up to where I was at. Oh, what? Hold on just. Okay, so at this point, we've created a point set of interval velocities within my, is this in case my second layer and my third layer, and these interval velocities are extracted from the seismic data. They're converted from stacking velocities to interval velocities. Okay, and now I can display those extracted velocities that are, again, in between this layer here, and we think that's the best possible interval velocities from the seismic. Again, it's this point set that only shows up where we have the 2D seismic velocity information. Okay, and we can either display the point set as its time representation, or we can display it as its velocity representation. Okay, and then if we look at it in the map view, what I can see is I've got some fast velocities, particularly on this line here and maybe that line right there. So I might want to look at those, see, okay, should they really be that fast? Okay, but now once we have these seismic velocities for our second layer in this case, we can go through our same little workflow and grid those up. We can do some analysis. Okay, do those, the histogram of the velocities within this layer, does that look reasonable? Okay, we can do some variogram analysis. If I know how the velocities should trend, basinward or, certain pressure regimes, I can set my variogram and my velocity interpolation parameters so that, that the velocities will be interpolated along a certain elliptical variogram. Okay, so that's, very good power for the user who's trying to create velocities and they want to actually have some geological control over velocities. I can set the grid however fine or dense that I want, but when I click run, I now have a velocity surface that covers this entire layer for interval velocities based upon the seismic data, the seismic velocities. And the seismic, again, doesn't necessarily tie the wells. We don't necessarily trust the absolute values of the seismic data. What we do trust is the trend of the velocities from the seismic data. And what also shows up is the error that we think came from the interpolation of these velocities. Okay, so right there, this is a map of the errors. The cool colors are little error, and the hot colors are lots of error. So again, wherever we have data, we have very little error. But in between the data, we think, we're really not sure exactly how much error we have between there. But at least we have a quantification of the error with these the error maps that are automatically generated via the property modeling tool used for velocity modeling. Okay, so now if we're happy with our at least seismic velocity interpolation, we can actually build a velocity model by adding this the seismic velocity that we just gridded up, and we'll create that velocity model. And I'm calling it. This is it's untied. So these seismic velocities have not been tied to the wells yet. We're just creating a model with raw seismic velocities. Okay, and once we've done that, what we could do is, we could, first of all, we could just take a look at it, what it looks like in the section view. And again, this is just a 2-layer velocity model. So we've got our velocity model that we tied to our first layer, and then we're trying to figure out the second layer. Can we get velocities that will properly tie this second layer? Okay, and to tie that second layer, what we want to do is we'll go into our geostatistical velocity modeling workflow again, and we'll say, okay, between my first layer and second layer, let's do a zone analysis. Okay, and I want to say, within this zone, how do I correct the velocities so they actually tie the wells? And when I do this zone analysis, what I see is, boy, I don't actually tie the wells. I've got a big old bias here. But what I do know is if I change the velocities by a certain amount, that will tie me to the wells. Okay, so I want to take essentially what I want to do is I want to take my seismic velocity surface and update it with these new changes in the velocities, and I want to geostatistically update this so I can snap my seismic velocities so that they will tie the wells. So again, I go into the property modeling, and I'm going to correct the mismatches. I'm going to correct my initial seismic velocities with my delta velocities, and then I will have this layer velocities that will actually tie the wells. Now, if I've got some extreme values here, I can do some geostatistical analysis. You know what? I don't believe that the velocities were 6,000 feet per second too slow, so I will trim those off when I do my updating of the surface. So I might want to go back and look at those particular wells that were not so good. Okay, and I can do, again, my variogram analysis or however I want to parameterize this. I have full control over how these velocity updates are being applied. All right, so now I can compare my fixed velocities to the non-fixed velocities. And fixed means the velocities tie the wells. Non-fixed means they don't tie the wells. And you can see how they were kind of wobbling back and forth. But now, for my second layer, I now have velocities that should tie the wells at the second layer. So now I can rebuild my velocity model in the second layer that will be tied to the wells. And again, I'll have to go through this for each of the layers to sort of layer strip and step down through to get each well tied properly. Now, after I build the model, we can just compare. And again, it doesn't look a ton different. The main difference is that these velocities now tie the wells where the previous one didn't. So for my next iteration, I'll do it for the third layer, and then I'll update this layer independently. Okay, so we've gone through and we've corrected these velocities. and at that point we could really stop because we've got a great velocity model that ties the wells. The problem is, it's not necessarily a problem, but we just built a single velocity model that tied the wells. But in reality, there's thousands of velocity models that could equally tie the well data, depending on how we interpolate the velocities in between the wells. So what we've added here in 10ep.3 is the ability to do stochastic uncertainty modeling of all of the velocities within the surface here. And all I have to do this is I change my algorithm from kriging to expectation with uncertainty. This tells me to do a bunch of stochastic modeling. We're going to generate over 100 models, and I'm going to call this my velocity uncertainty models. We're going to run through the kriging essentially 100 times, and that's going to give us 100 different models, and then we're going to sort these models, and we're going to come up with a P10, P50, P90 model, and we're going to get a mean model too, where we're going to just average them all together. So, if we look at this, the mean model is a little bit smoother than the rest. Here's the P90 model. So this is meaning the P90 is my fast velocities, and then I can also show some what the errors look like for the velocity model. So right here, this is the errors of the velocity model if we don't take the data into account. The error is based solely on the shape of the variogram and the location of our control data, which is the wells. Now, if we do the stochastic simulations, our errors map completely changes because it's not only a function of the variogram and where the wells are, it's also a function of the data. So this is a much more accurate error map of how much the velocities are changing. And it's actually, the error is much less when we do these the stochastic simulations here. Okay, so it's giving us some good uncertainty modeling. Now, if we can compare the models actually side by side, and in this case here, we can compare my slow velocities versus my middle velocities versus my fast velocities, and see, now again, all these models equally tie the wells. It's just they're interpolated differently between the wells. Okay, so they all could be valid. We tend to go for the P50 model or the mean model, which is the average of those, which is just maybe a little smoother than say like the P50 model. But in any case, we've done all this great analysis. We now can generate different velocity models based upon these scenarios. So I can build a velocity model based on a P10 velocity simulation, a P50 velocity simulation, a P90 velocity simulation, and then we can run those different velocity models through some reservoir simulations to give us P10, P50, P90 volumetrics. So this is a very powerful workflow to get a good, what we think is a good geological, geophysical handle on the volumetrics based upon perturbing the velocities with this method here. Okay. Now the final piece of the workflow that we've added is what we're calling the velocity zone analysis. And this is a bit different than the previous workflow, because the previous workflow we were in an underdetermined case where we're trying to get the best velocity model over an entire basin with little control. In this workflow, we have 3D seismic data, we have lots of wells, we have lots of control, and we want to get the best velocity model sort of within this layer. And the issue that we have in what I'm calling the overdetermined solution is I have, say, a depth point right here, and I have a check shot, so that tells me the velocity. But I also have a well pick and maybe a time surface, so that tells me the velocity. Well, I also have a depth migrated surface and some depth picks, so that tells me the velocity. I've got seismic stacking velocity, so that tells me the velocity. I've got a whole bunch of velocity information that's all somewhat conflicting. And I tell people about the overdetermined solution. It's like if I have one watch, I know exactly what time it is. But if I ask 10 different people what time it is, I get 10 different answers. So at that point, I don't know what the time is. Well, here, I'm not really sure what the velocity is if I have all this conflicting information. But of course, if all I care about is the well tie to the pick, I can just use the depth pick. But it's critically important to know how the velocities change within the layer if you care about seismic imaging and seismic inversion. Because if we just put a constant velocity here that ties the wells, there would be the seismic would travel straight through this layer. Now, if the velocities are actually increasing with depth, the seismic ray would be curved through this layer, or if there's some sort of inversion, we'd have some sort of nonlinear seismic ray through this. So if we want accurate seismic images, we need the accurate velocity modeling in between the layers. And again, if we want to do depth conversion in between the layer, it's important to know if the velocities are increasing or decreasing within the layer. Okay, so I will just go straight into the demo for this guy, and I'm going to show you how we figure out the overdetermined case for the velocity modeling zone analysis. Okay, so using our same data, we can select a zone to do our analysis on, and basically our analysis we want to do is on the interval velocity. Now the neat thing here is we can dynamically define the zone. So here I'm going from the Carly to the tin sleep, so maybe a thicker zone. I can make the zones thick or thin depending on how quickly I believe my velocities are changing within my geologic layers. I can pick my time depth curves that I want to use for this analysis, and I can pick whatever seismic velocities I want to use for the analysis. And they can be velocity models, they can come from processing, they can come from a processing shop, from a contractor, from whoever. We can get those velocities in. And then the beauty here is now we can cross-plot all of the data, the pink being all the seismic data, the green being the well pick velocity data, and the blue being the time depth curve or check shot data or VSP data. Now, if I hover over a particular well or a particular point, I can see exactly which well that came from. So that gives me a little bit of anomaly hunting where I can see where the wells are coming from. But in this case here, I've got depth on the vertical axis and interval velocity on the horizontal axis. And I'm just within one layer, so I'm going to just draw a line here to say, okay, this is my trend, at least what the seismic is showing me, how the velocities are increasing with depth. So as soon as I draw that line, it automatically populates what the equation is of how the velocity is increasing with depth. Now, if I did some research on this basin or on this layer, and there's publications that say, oh, well, within this layer, within this basin, the velocities should increase with depth based upon, this slope and this starting velocity, I can simply type that in and watch how that shows up in my zone analysis here. Okay, so I can compare lots of different data types in this same crossplot. Now, the question is, where do these points actually exist in real life? Because here I'm just in the crossplot world. If I just do a selection, a polygon selection or a box selection, when I do that, watch what happens for the point sets. So now what I've created is a point set of all my velocity information from the seismic, from the wells, and from the time depth curves, and I can see those in my cube view. I can also see it in the map view and the section view, but here we get to analyze the velocity trends based on all my wells, so I don't necessarily have to have check shots for these wells. I can see what the seismic velocity trends are and my pseudo-velocity trends are. Pseudo-velocities are based on picks and seismic times. Okay, so we have lots of nice ways to QC our velocities within the layer. Okay, so are the velocities increasing or decreasing within the layer, not just a constant velocity within the layer. So it's very good detailed zone analysis. All right, so I know that was a lot to go over. We talked about the overdetermined case of getting the correct and best velocities within the layer. We talked about the underdetermined case of getting the best velocity models for regional prospects and petroleum system modeling. We talked about sort of the subsalt funhouse mirror effect of correcting velocities and depth conversions, and then just general usability within velocity modeling. So it was lots and lots of work, but that's the main gist of what we did in velocity modeling. I thank you for your time, and I'm ready for questions.